Bom, boa tarde a todos. A gente vai dar início aqui ao nosso colóquio, mais uma vez. E sendo... Tá dando um microfone aqui. Oh, yeah. So I'm going to move it to Professor Gabriel Landi that are going to do the introduction for our speaker. Gabriel.
Okay, hi, good afternoon, everyone. So it's a great pleasure to introduce Irene D'Amico. So Irene did her bachelor's in Italy and then her PhD in the US. And then for a few years, she's been a professor at the University of York, where she coordinates this Center for Quantum Technologies. So Irene has visited Brazil many, many times, especially São Carlos and UFABC. And this is her first official visit to this campus in USP. So finally, she, I think, completed the whole cycle of all major universities in São Paulo. So it's a pleasure to have you here. Thank you very much.
Thank you so much. Thank you so much for the kind introduction and in general for the very warm welcome. Thank you all for being here. I hope you will be still happy by the end of the talk. So as it was said, I have been a few times to Brazil. I've been once at USP Sao Paulo before, but it was one of these formal visits with my university. So I didn't have actually the pleasure of visiting physics that time. So I'm very, very pleased to be here. And thank you again for the hospitality of Gabriel. So could you hear me? Okay, so I will tell you something about applications of many-body non-equilibrium dynamics to quantum technologies. This is quite a mouthful. And so to give you an idea a bit where I come from and how all these things get together, let me go to this Venn diagram. And what I'm going to tell you about sits in the intersection between these quite big areas of research, many-body quantum systems, non-equilibrium quantum dynamics, and quantum technologies. And this also represents a bit my background under various collaborations and during the years. So within this intersection, actually, there are many sub-disciplines or sub-area of research. A part of them, at least, are in this intersection. For example, quantum computation can be seen as driving a system out of equilibrium in order to perform some kind of algorithm, at least in the standard gate-based implementation. A good part of spintronics also looks at many-body systems which are out of equilibrium, and both of these are quantum technology. Part of the studies related to entanglement, for example, dynamic creation of entanglement, dynamic generation of entanglement, and others are definitely many-body and often involving both non-equilibrium and, of course, quantum technology. Similarly, quantum sensing. Quantum dynamics is even worse because you also have to turn on the temperature, and that also complicates things. I mean, officially, you need to turn on the temperature, and so complicate things even further. And the coherence definitely has to do with many bodies and with the fact that your system is performing some kind of dynamics that is not what you would like it to perform, if you like, and is very important for quantum technology. So this is just a list of subdiscipline which somewhat, in part at least, fit in this intersection. And what I will be telling you today is related to two of these. I will be talking a bit about quantum computation, and specifically I will be talking about modular and distributed quantum computation with qubit networks. This will be the big part of my talk. And then if you're not too tired and the time is not too late, I may go on and tell you just a bit of our relatively recent results on quantum thermodynamics, and in particular looking at many-body effects in quantum thermodynamics. So let's start from modular and distributed quantum computation with qubits network. And I will try and explain you the meaning of all these keywords in the title. Let me start with modular quantum information processing. So as we know from our traditional computer, I don't want to call them classical because actually there is quite a bit of quantum mechanics going on into these machines. So let me call them traditional. To solve problems, usually we need, thousands and thousands, millions of bits. Well, it's not so different for quantum computer, actually, if we want to solve real-life problems, especially because of the request for error correction. And if you like, the request of basically additional qubits in order to safely encode a logical qubit. So really, you will need quite a bit of qubits also for having a functional quantum computer that can compute something, really, really beyond what we can with a traditional machine. And we are also in a very, at the moment, in a very exciting moment, that is, we have finally some substantial devices, some substantial quantum processors of the order of a few tens, even 100, or even very recently, few hundred by IBM qubits. And this go under this type of devices, go under the name of noisy intermediate size quantum devices. Intermediate size is clear because of the size. Noisy because of two things. One, again, the machines are too small, too few qubits to implement really error correction. And two, we are still learning, well, more experimentalists, but also we theorists do something in that respect, to actually stabilize in many sense this type of machines, so helping to go against the coherence. So when we want to take all of this into account, we can imagine that as it is for our traditional computers, our actual quantum computer will not just be one huge chip, but will actually be more of a modular type of device. So we will have, maybe each of these could be the size of one of our noisy NISQ devices, or bigger, depending on what will be possible. And then we will have some quantum link relating, connecting this module. So in this sense, it's interesting to look for the future clearly at modular quantum information processing. So if we think of each of these quantum chip as, for example, a NISQ device, then we can think of it really like a network of qubits of a certain size, okay? So again, within here, I will have a number of qubits within each of these chips connected somehow, some of them connected to each other with some kind of connectivity, so a network. One second important element is this quantum link I was talking about. Now, maybe a difference with traditional computation, it would be nice to think that this quantum link can do something more than simply bringing information from A to B. So in this sense, we could think as to some kind of distributed quantum information processes. So we would like this link, for example, of course, to be able to transfer information with high fidelity. But also, for example, if this is chip A and this is chip B, we would like to use it to create entanglement within the two chips. Or even better, we could use it to make some kind of operation, quantum gate, between some qubits here and some qubits there. When you think about all these possibilities, you can also root and so on, you can think of this quantum link, again, as something a bit more complicated than a simple string, for example, of qubit, but something with a bit more structure. Doesn't have to, but it may give us advantages. And so we can think of this quantum link also as a qubit network with some functionality, so a functionalized qubit network, like the ones I've listed here. So I hope that this has convinced you that it's quite important then to look at these qubit networks, not too big, not too small, with the idea of being able to functionalize them in a way to do certain quantum operation. And we have some wish list for this. So first of all, of course, we would like it to perform the operation we want, and possibly in a time that is short enough with respect to the coherence, and the time that we know, because we would like to have some kind of clock in our system, or at least know when we have to go and, for example, pick up a state from a certain output. We would like it to be quite resistant to the coherence, and in particular, if you think about building this stuff in a lab, you would like it to be resistant to fabrication error and maybe to fluctuating field, I mean, things that you often find in a lab. You would like it to do the desired operation with high fidelity, so that you can trust that at the end you have high probability of actually performing the algorithm you like. And because qubits are still quite expensive, it would be also nice if we could reprogram the network, so hopefully use it for different functionalities. In order to keep the coherence down, the least you actually interact with your qubits, the better, because you may avoid to have, for example, fluctuations in the driving fields or any sort of interaction you actually don't want with your qubits. And so in general, you would also like to have the possibility of doing all of this without necessity of a big tuning or big control, and also without having to perform too many operations. Usually, for any operation, you have an associated probability of error. So, for example, if you want to go from a qubit here to a qubit here, you would do it transferring information. You would like to do it in a smarter way than doing a swap between, I don't know, the 100 qubits in the middle, because then by the 100 swap, your probability to perform an error is quite high. So these latest two things, you can think of doing them by, or helping with them, by exploiting the natural evolution of your system. So your system will have natural, your system is not something abstract, it's actually a physical system sitting in a lab for now. Could be cold ions, could be electrons in quantum dot. I mean, you choose your hardware. And so it will have a specific Hamiltonian, which is characteristic of the system. So ideally, we would like to use that characteristic Hamiltonian and the evolution generated by this characteristic Hamiltonian in order to do good part of the operations for us. And this is great, except it's a little bit tricky. So let's think about our network. And let's say I want to, simple operation, transfer an excitation from the input side to the desired output. So I start in this way. So everything is at 0, my excitation, I flip simply this qubit here. And then I let the system evolve. So I wait, I sit and wait. And the most likely outcome is that my excitation spreads all over. This is because this is quantum mechanics. It's not a ball rolling. You have a wave function that will start spreading. So we need somewhat to engineer quantum interference in order then to be able really to, inject our excitation, wait a time I know, and then in this case, get the desired output with 100% fidelity or almost 100% fidelity where I want it. And so this is about what the talk basically is about. So we are not the first that have started thinking about using natural dynamics of the systems in order to perform operation. Probably the first review was the one by Bose in 2007, that people had already started working on this type of idea. There is a big literature about various things that you can do with qubits network using the natural dynamic of the system, for example, transferring information, quantum information from A to B, generate and or distribute entanglement. You can route information about various quantum processes. And in this respect, we have, we have just published a paper in which we describe a device that does a bit of everything, and the way actually to design a series of devices that could do a bit of all this operation, but I will not talk specifically about this. So there is quite a few people working on this. One thing, let me just, including some experimental work, for example, on this type of spin chains. Let me just stress one thing for the people that are not working on quantum technology specifically. I will interchange the word spin and qubit because you have a one-to-one mapping between spin 1/2 and qubit. So I will use, you know, the word in quantum network, qubit network or spin network, interchanging the two, because we have this type of relationship. So what I would like to tell you about today is our work in this last couple of years on actually building an evolutionary code, so a genetic algorithm type of code, in order to be able to design devices with the type of characteristics I have described before. Why this? Well, as I mentioned at the beginning, we have that our networks of qubits are becoming bigger, and with that, the parameter space is becoming exponentially larger. So it's becoming more and more difficult to find an analytical way to actually understand the properties of these Hamiltonians with so many parameters in order to obtain the functionality I want. So in this respect, having an efficient way of exploring this parameter space with a certain objective function is, if it is efficient, actually something very welcome. And that's what we have started doing with our genetic algorithm. And it's not just useful for designing devices, but also for new, I mean, it's basically a very similar type of operation. If you want to calibrate a device, also you would like to optimize your configuration. So the idea is, in this way, our evolutionary algorithm will give us as output a parameter configuration for a given network, so that this network can perform the task I wish in a time that is known. And it will exploit the natural dynamics, so the Hamiltonian of the system. And it is platform agnostic in the sense that all it knows is that it is dealing with the network of qubits. So as long as you can map your hardware into a network of qubits, which is the case if you're trying to build a quantum computer or a quantum processor, then it can work. And of course, additional functionalities can be added to then adjust it to different hardware. But this is if we would start working in collaboration with an experimentalist specific hardware. So the type of Hamiltonian we are using is the XXZ Hamiltonian. It is characterized by these three terms. We have a hopping term, which makes our excitation hop from one side to the next. The next by next, I mean the one directly connected to it. We have on-site energy, so this is something you could control, for example, with a gate on top of your qubit. And then we have this term here, which you can see as a dipole-dipole interaction. And this term will act only if you have at least two excitations in the system. By excitation, I mean two spins, altogether 2-qubit set at 1, I mean, when you calculate, when you look at your Fock space. And the Hamiltonian is time independent, clearly. And so it will, the task will be achieved by natural dynamic. Of course, other Hamiltonian could be implemented. In principle, we have not done it because we have been playing with this Hamiltonian for a while now. So it's the one we have decided to use, and also maps to a series of hardware. So this is the flowchart of the genetic algorithm. So again, the input is what you want your network to do. For example, create entanglement between two design qubits, and how many spins you have in your network, and the type of connection. So who is connected with whom? Even this could be released. I mean, it could be changed as a condition, but this is something we are using. And then the clever bit was to find a way of mapping, of writing the state of these parameters that describe in the Hamiltonian that describe the network as a genome. And then we can create a population of this genome, the first generation. So we basically create a set of Hamiltonian, where by set of Hamiltonian, I mean Hamiltonian with different J's, epsilon, and the other also is called, I think, J alpha. And then what we do, we run our simulation through all these genomes and see which is the best under the conditions, which I will explain better later, that under the constraints we put to the system. One of the constraints is clearly that we would like high fidelity for the operation we want, but this is not the only one. For example, it's also important that it will not take forever to do the operation, because then we know the coherence will kick in. And so, I mean, so basically we rank through the fitness function all the genomes in this first generation. And then according to the, mainly according to the value of the fitness function, we choose two parents, we breed them, and we create a child. And then, not happy about that, we also insert some mutation with some kind of probability. And in this way, we create basically the new generation. So we start with 1, we arrive to generation 2. And then we check if we have, the way we stop the code to run is once we are running to a certain number of generations. I think it's 200 at the moment is what we set, just chosen because it works well, but I mean. And so if we have not reached the limit, we go on with this cycle. If we have reached the limit, we go out and so we go back and we go on with the cycle, and we check which is the best genome over all the ones we have explored, and that will be our solution. And so basically the solution corresponds to the parameter of my Hamiltonian in order to perform the functionality I have chosen the best under the constraint I had and under the, for example, the number of generations I have explored. You can always refine it with further run and generation and so on. So this is the fitness function that we are using. This was the other clever bit. And the clever bits are from Luke Mortimer. He was doing an integrated master with us. Very clever guy. And so just to say, I say clever bits and I refer, he's the one who found them, and that was really great. And as you can see here, here we have two terms. So the first term here in the fitness function will give me a number between 1 and 100. 100 is very, 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 very good, exceptionally good, the best. 1, really, you don't want to use it. So the first term here favors high fidelities. A here is positive. So the closest this is to 0, the closest this is to 1, the closest this is to 100. Okay. The second term here, instead, is trying to keep the time down. So beta here is negative, So the larger is my time, the more I have an exponential damping, and the smaller is my the value of my fitness. And so you can see that there may be, not always, but there may be a competition within the terms. But both of them are important. And so let me show you some results. This is what we call the multitask shoelace. A shoelace because it reminds us of a shoelace. So this is the network. Don't look at the number of on the links. These are part of an optimization, a particular optimization. Just look at the shape. So the shape and the connectivity was our input. And as you can see, we asked this particular network if it could do a whole series of tasks. I will explain some of them. These are written in the way we write our request. So, for example, the first one of them is having inputting an excitation in A, wait a known time, and getting the output in E. And indeed, we can do that with very high fidelity and with relatively short time. All of these are pretty short times. This is the time that the system would need to perform the operation, just to clarify. And something more complicated, we input an excitation in C, wait a known time, and then we want to have that A and G are entangled. Yeah, we can do that, and we can do this in two different ways. So this is a different phase between, if you like, a singlet and not a singlet. Okay, and so on and so forth. Also this with very high fidelity, and so on and so forth. So as you can see, what was interesting for us was discovering that even a relatively simple device like this could be not only reprogrammable, could do a number of tasks, some of them really non-trivial, and with very, very high fidelity, and in times when measured with respect to the inverse of the strongest coupling in the system, which is a natural time for the system, times that are most probably within the decoherence time, because in the other case we would have problem. I mean, the experimentalists would have problem if the decoherence time is not at least a few tenths of time above this natural time. So we did then decided to do something more complicated. And so we got excited and we said, okay, can we actually do some properly distributed quantum computation? So we took this network here. Again, don't look at the numbers, look at the shape of the network and the number of spin. We chose this simply because we thought that's probably something easy to build in the lab, something square with two input. Okay, the idea is that this is my, okay, let me go back. Two input and two output, okay. And then the idea is, can we make the Hamiltonian of this system, so just changing the parameter, tune the parameter in a way that this network performs a control phase gate, which is an entangling gate, between, you can imagine of having a chip A here, so this is my input from chip A, and the output will end up instead in chip B here, so distributed computation. So again, the idea is that this is my input. I wait a known time sitting there, and then I collect the response. And of course, the answer is yes. In the other case, I would not be here telling you the story. We were very excited about this. And one thing I would like to underline here is that doing the quantum gate, a 2-qubit quantum gate, implies something a bit more complicated than we did before. Because to do a 2-qubit quantum gate, so this is my truth table, you have to have not only that each one of these operations is performed with very high fidelity, but also that they are performed at exactly the same time, because your input could be in a superposition of any of this, and you want the output to be the correct output and arrive all at the same time. So it was quite exciting. Yes, we could do that. And the time, again, was of the order of 10 times. I mean, 12.4 is what we find, as I said, is natural time. And then we realized something even, well, we don't know, okay, something that we found even more, more interesting. So we do usually our computation with 4 significance figure. That means we use 4 significant figure to determine the value of our parameter. But then, you think you go to an experimentalist, and experimentalist tell you, yeah, 4 significant figure, please go away because, I can tune a bit, but not at this accuracy. So from there, and we didn't recalibrate the system. So we took the result from the 4 significant figure, and we simply approximated the parameter. So without redoing the optimization, we go to 3 significant figure, again, without redoing the optimization. Fidelity is still excellent. We go down to 2 significant figures, still excellent fidelity. We have to go down really to an experimentalist that tell you, I can just, it's 1 figure you have to tell me, to get really a fidelity that is not so good, really. I mean, but it's still in the 80s. So this type of, and this robustness is something that we have found in various of our devices. We don't have an explanation for it, but we can see that they tend to be quite robust with respect to what you can think of fabrication defects. And again, this is a quite complicated optimization because we have 28 parameters in the system. So more recently, these are the very recent results, which has been, the work is still in progress. We have not published this one yet. Another problem that we have been looking to is the transfer of an excitation along a chain, a linear chain this time. So we input here, we wait, and we collect our output here. It's just a transfer of a quantum state. And this problem is something that is known as perfect state transfer, and is something that has been looked at since, I think the first paper was 2004. And then there was the one by Chris Tandall et al. Is usually, there is an analytical solution, but there is an analytical solution which modulates the J's. However, there are certain type of hardware in which you may think the J's are not so easy to be modulated. It may be more easy to actually modulate the on-site energies, the epsilon. For example, if you have trapped ions, you can think that your J's are defined by the interaction, the Coulomb repulsion, and you can instead maybe modulate with the gate the energy of the local energy of your trap atom. And so that's what we have done. So now we are looking at a chain which has a constant Jij, but we ask the genetic algorithm to modulate the epsilon i's in a way that we have a perfect state transfer. And indeed, we find a solution. The solution, so these are the on-site energy. They are rescaled by the maximum one so that they all can be fit nicely in this plot. For different size, and the chains are from 4 to 7 here. You see that more or less they have a parabolic structure. And when you look at the spectrum instead, so now this big here is actually are the eigenenergy, not the on-site energy. You find that the spectrum is actually quite regular. It is equally spaced, except for the last interval. And what was more interesting is that at difference with the solutions that are known for the case in which you modulate the J's, we actually found families of solutions. So this is the case, for example, for n equals 7, these are 2 solutions. And what we have understood is that, and also understood somewhat analytically, in the sense if you impose mirror symmetry in your chain, which you need to have this type of periodic motion, and you look at the evolution of your states, this, of course, after having seen the numerics, you realize that basically a way to get back quantum coherence in a way that your excitation is exactly reconstructed at the end of the chain is that the ratio between the last energy interval and the previous one, this object here, is an integer. It's an integer, so they are commensurable. But is an integer, doesn't tell you which integer, and that's why we have we realize we have actually a set, families of solutions. So here there are some numerical results for two families. The red one has this ratio here equal to 3, and the green one has this ratio equal to 5. And okay, so this was the first part of the talk. Do I still have some time, or do you want me to? Okay. So the second part of the talk, let me just get some water, is related to a completely different, well, completely a different subject, but still in this intersection between many-body theory, non-equilibrium dynamics, and quantum technology. And this is related in particular to many-body effects in quantum thermodynamics. So I will keep this part quite short. I will just show some results. Let me just give a bit of introduction. As I'm sure you know, I mean, you have a very good colleague working on the field here at USP, for example, Gabriel. Quantum thermodynamics is a bit of a booming field in these last probably 10 years. And it deals with, on the one side, how to transfer concepts we are very familiar with, like heat and work into the quantum systems. And there are hot, heated discussion about the definition of work and heat in a quantum system. So that is where they don't become so familiar or well understood yet. But also there are questions how to go from, from the point of view of thermodynamics, from these quantum properties that we see to the one we are used to in, let me refer to as classical thermodynamics. By now, there have been a number of proposals for devices, like engines, refrigerator, batteries, and so on. Interestingly, in these devices, not only thermal fluctuations are important, but also quantum fluctuations. So, for example, due to measurements and collapse of the wave function. Interesting point can be, thinking of using all these qubits, all these very small quantum systems to harvest energy. Or conversely, you could actually think of using your qubits as devices, for example, as engines and so on. This is something that people have started to do. You can also think of the problem of heat in a quantum computer. So you will need to cool it, and maybe so you can use a quantum refrigerator for cooling your chip. Or you can look at the algorithm from a quantum thermodynamic point of view and evaluate it in a way that, for example, it consumes less energy, produces less heat, and so on and so forth. So there are a number of interesting questions related to quantum thermodynamics. In particular, something that is important for the few results I'm going to show is the difference between the probability distribution function in our standard thermodynamics and in our quantum thermodynamics. So in our standard thermodynamics, we are used to deal with probability distribution, for example, the probability distribution of work, which are usually Gaussian or anyway bell-shaped, are nicely behaved with a single maximum, pretty narrow. The width is usually given by temperature fluctuation. You can see effect of the transitions in this distribution and so on. When you go to the quantum regime, things change because you have often just a handful of degrees of freedom. So you're very far from your nice continuous distribution. You start to see a series of peaks. There is maybe not a single maximum, definitely often not a nice bell shape. You have the quantum fluctuation. You can wonder, how do you go from this picture to that? This is a question that is still open. And also you can wonder about the effect of quantum phase transition on can I actually witness quantum phase transition looking at probability distribution of, for example, quantum work in a quantum system. So we've done some work on this. The system I'm going to deal with now is different from before. These are finite Hubbard chains. Finite because we do exact diagonalization. So we cannot do an exact diagonalization on an infinite inhomogeneous chain. So it's exact diagonalization of inhomogeneous Hubbard chains, which is non-trivial. And we also do exact dynamics in this way of these chains, which is also non-trivial. And this is our Hamiltonian. We have a hopping term up there, which again is hopping from over fermion, this is fermionic from one side to the next. We have on-site many-body interaction. We have an external drive. So somewhat we shake the system. And the type of drive we have, if this is our chain, we tilt it. We tilt it in a certain time. The time is finite in this first part. And the system is closed. So depending on how fast or how slow I tilt my system, I will have an evolution that can be adiabatic or an evolution that can be close to a sudden quench. Okay, and we looked at all the variations in the middle. In a closed system, the work is simply the difference between the initial and final energy. And to it, we can associate this probability distribution, which simply tells me that initially I am in each of the terms tell me that initially I start in a specific state of my initial Hamiltonian. This is because basically to get this energy, I need to measure the system twice. So initially I collapse my system in one of the eigenstates. Then I let the system evolve under the drive, and so I will have a certain probability of transition to a state M of my final Hamiltonian, given, of course, that initially I was in the state N of the initial Hamiltonian, and finally I have to take care of energy conservation. So this is the structure. And I will look at two different transitions. So first of all, with this type of dynamics in which I tilt in this way my only once my chain, so it's like having a transient current, if you like, what we do. We will look at the case in which we have repulsive electrons in the system, and we are at half filling, and basically we will look at the precursor of the Mott-Insulator transition. And then later on, with a different type of dynamics, which I will briefly discuss, instead we will look at the case in which we still have fermions, but with attractive interaction. And we will look at the superfluidity to insulator transition that is triggered in this case by increasing the disorder in the system. Okay, so these are the results for the case of the Mott-Insulator transition. Here, on the left-hand side, you have a system with 4 particles and 4 sites. We are at a filling, 8 particles and 8 sites. To give you an idea, here I have 16 transitions. Here I have 5,000 squares, so it was 25 million transitions. So this is huge with number of transitions. And immediately you see that, oh, great, I go from, by increasing, I am at, it's non-interrupting the system. By increasing the number of degrees of freedom, I go from something that looks like this funny shape probability distribution to something that looks like a much nicer bell-shaped distribution. And I'm sweeping to the different dynamic regime. Here we are close to the sudden quench. Here we are close to the adiabatic regime. And here you can clearly see that the distribution changes depending. You see that some peaks come up and some go down with the type of regime. But now we turn on interaction and we go on the other side of the transition, and things changes dramatically. So you immediately see that clearly the distribution picks up a signal of the transition. The number of degrees of freedom have not changed, but now the two distributions are not very different. And also they are not really dependent on the fact that you are doing something that is a sudden quench or something much more adiabatic than that. So from here we thought, okay, this is interesting. And so we went and looked at the moments of the distribution. So this is the mean. This is the width of the distribution. This is the skewness of the distribution. This is the first moment in the distribution which tells you if your distribution is symmetric or not with respect to the center. And this is the fourth one. And yellow means that we are almost adiabatic, and here we are closer to the sudden quench. And here I'm sweeping with the interaction. So here I'm non-interacting. And when I'm here, I am basically past this quasi-Mott-Insulator transition. I remind you, it's a finite chain. So the full transition is at the thermodynamic limit with infinite chain, but you can clearly see the precursor here. And the biggest sign we see, first of all, when you look at the moments, the picture is basically the same for the 4 moments, independently on the number of degrees of freedom. So for n equal 4 or n equal 8, even before you saw that at least in certain cases, they look very different. Well, qualitatively, they're very much the same when you look at the moments. And the one that really seems to pick up the transition, remember, the transition occurs here, it's not sharp because it's a quasi, as a precursor, so it occurs here, is the skewness. And you can see that the skewness goes from negative to positive. So really, your distribution first is skewed this way and then goes skewed the other way across the transition. One thing that is interesting is that this signal is very big when you look at finite dynamics. If you look here, this is almost sudden quench. You basically lose your signature, good part of the strength of the signature. So this was also something important. This was done with finite dynamics. So let me briefly move to last couple of slides. And so I will move to the superfluid insulator transition. And this is something that was seen experimentally by Chin et al. In 2006. And it was then studied theoretically by Canella and Franza. In this paper, they studied the entanglement, the behavior of the entanglement in the system. So again, we have a number chain, these are finite chains. And what we do in this case, we start from, the interaction is attractive in this case. So if you increase the interaction, you will have a superfluid forming. Basically, is a way of simulating the superconductor, type of superconductor. But if you trigger the, if you start putting impurities in your system and you trigger either the number of impurity or their strength, you can actually have this transition between superfluid and insulator, and that's what we're looking at. So, Canella and Franza showed that there is a clear marked signal of the transition at with the entanglement, which would go to 0 in the thermodynamic limit. Here we are looking at chains that are 100 site long. We are not at half filling, but this is the density. So we did the same calculation for the work in collaboration with Franza, Canella, and Krystian Zawolski. And what we saw is that indeed this transition is very nice signaled by the work, which is maximum when the entanglement is minimum. And so we just, the dynamic we are doing here, because of course this you can do without dynamics, but here you need a dynamic, is a sudden quench. And what we are doing, we are adding one impurity of the same strength in the system. So for example, we go from 2 impurity to 3. And here what we have is the concentration of impurity, is the initial concentration. The final point will have an additional impurity. And to look at the moments, we had to look at shorter chains. We find the same signal for the work. We find that the variance goes to 0 at the transition. And once more, we find the signature, in this case, also in the case of a sudden quench, on the skewness that changes sign with the transition. That's, I think, enough that I've said today. So let me just, okay, this just to show you that indeed this was at very low temperature. This is at high temperature, and you can see that we lose the transition. And these are the collaborators. So let me acknowledge the collaborators for quantum computation. These are the 2 students that Luke is the one who basically built during his master the genetic algorithm code, and Fatah is the one who is now working on the perfect state transfer on the spin chain, and Marta and Tim are my long-standing collaboration on this type of work. On the quantum thermodynamic side, Guilherme at the time was a student when we did the work on the SIT, on the superfluid insulator transition. And these are my other collaborators, Vivian Franza, Christian Zawoski, and Roberto Serra. And with this, okay, I leave you with the summary. Thank you very much for listening to me. Thank you.
The audience.
So very nice talk, Rain.
Thank you.
Regarding the Mott insulator transition in the Hubbard model.
Yeah.
So if I understand correctly, you changed the local V's at each site.
Correct.
And you tilt the whole thing so it
Yeah.
looks like that.
Yeah.
So what's the amplitude of this movement compared to U, for instance? And
okay, now I have to go through memory. U is varied between 0 and 10 in units of J. J is the Oppin parameter and is our unit of energy. The tilting, I think, is varied between, at the beginning is slightly asymmetric already, something of the order, I think, of 0.5 J. At the end, I think it's of the order of 20.
okay.
J, so it's a bit larger or comparable anyway with U, yeah.
But then the whole thing goes out of half filling.
It goes out of?
Half filling. I mean, it's not homogeneous anymore.
Oh, sure. It's not homogeneous, absolutely.
And
yeah.
still you have a Mott insulator at the end.
Yeah, we still see the
Okay.
freezing of the system, yeah, because of this, well, you say it does that. You see, the point is you have this competition. So U is still strong enough to freeze the system, if you like. So the final state will change depending, while the variation of the tilting is always the same. Okay, so the final Hamiltonian is always the same. Yeah, initial and final, well, apart from the value of U, but I mean, the type of tilting is always the same. This is important. The final state will depend on you, so you will see really the competition. So they are comparable at the end. Yeah, we have also actually looked at we have different type of dynamics, and we still see this type of effect in the system. But again, they have to be comparable. Clearly, if you then choose a tilting that is 10 times your U, I mean, it's a different story. Yeah.
Other questions? I have my one. So can you comment on the current limitations for the algorithm that you have developed on the genetic? For the algorithm that you have developed?
Sure. So let me go out of desk. So I can give you a few. Well, first of all, importantly, the algorithm is highly parallelizable, and as you double the number of your core, is really linear. I mean, your time goes enough, because you can imagine it's a number basically of, you can do them in parallel, all this genome checks. And so that's really, I mean, if you have a lot of cores, that's what we have seen as, now the scaling is something very difficult to check, because in order to do the scaling, to check the scaling, you have to have some solution, you know. So the only solution, and also you have to do it in a fair way. So the only solution we had analytically was the solution for the perfect state transfer in the case you modulate the J. This is known analytically. So we could, because we knew there was a solution for increasing the size of the system, we could check. However, we did the check in what we consider a fair way, so always with the same parameter, without optimizing the code every time for larger chains. Okay, we try to be fair, because again, there are a number of tricks how you could, because you could say, you know, I make the chain longer and I play in a different way. So when we looked at that, it's not bad. What we find is that it's weakly exponential with the number n, not weakly. So the exponent is, I can show you the graph, it's probably easier, because also there is more information. This one. Okay. So here we are looking to chains up to 32, so quite long. We have 32 parameters to optimize here. Okay. We find a solution. We know there is a solution. This is the one I was saying. And you can see here the solution in how this curve goes. The exponent is like e to the 0.1, e to the 0.2. It was so very tiny. So, and again, every time you double the number of your cores, you divide by half the time. One other important point is that the optimization time, this is in seconds. Okay, so you have done 32 parameters at 97% fidelity in 40 seconds with 4 cores, would be 20 seconds if you have 8 cores. If 95% is enough, then you dramatically go down in time and also in the type of, and if you'd say, okay, 90% is enough, clearly you go down dramatically. So it's actually not bad. And already, if you tell an experimentalist now you tune this many parameters, probably is going to, I don't know. The other question that is connected to this is how does it compare to other algorithms? And that's an even more difficult question to answer, because I show you what I have in that respect. Because again, the problem is to make a fair comparison, you should compare for exactly the same optimization.
Exactly.
Yeah, which is basically not really what you can do. So,
but for sure, you can already see the advantage to it, for the implementation. So first of all, we are the only one, well, we found then another paper that have done something similar, but it just does one. I will arrive at that at the end of this slide. So first of all, the only other comparison we could do when we did it was with randomized search. And with randomized search, so now we look at a linear chain that is 10 spin long, 9 parameters. Our algorithm is 5,000 faster than randomized chain. So that's quite a bit. So then they ask us, what about machine learning? The referees, of course. That is obvious. I mean, everybody would ask, right? So, and it's difficult to compare because there was, for similar tasks, there was very little. And what we found is that there was a paper where they were tuning 8 parameters in a quantum dot system. Something different, they are not our chains, and every problem has a different type of timing, but also they compare to randomized search, but their increase was only 180. Now, I say this, but I don't know how comparable they are, because this might have been a much tougher problem to solve So it's complicated. And if we compare with the number of parameters, they took 4,200 seconds, and we took something depending again on what we were optimizing, 5 seconds or 0.6, depending. So what I can say is comparable. After we published the paper, we found this paper here, which is very interesting, and is the only one we found which does something similar in the sense that also optimized PST. It uses reinforcement learning. It does, but gives only one result, 450. It optimizes it with respect to something different. It optimizes it not with respect to the analytical solution, but optimizes velocity, which is again a different problem. On the face of it, it looks faster than our, but it just gives you, doesn't give scaling, doesn't give detail. And also, as I said, we did not optimize for increasing length of the chain because we decided we want to see the scale. So this is the data I have. It seems to compare pretty well, at least on the order of a few tenths of parameter. Definitely is very fast, and it's found solutions that were absolutely unknown. So in that sense, we are happy. And now we hope to, there are lots of improvement that can be done in the algorithm. And so we hope to, move on with it. Yeah.
Great. So further questions?
Hi, Irene. So I was wondering, so you showed in the shoelace problem that you could achieve very high fidelity in reasonable times. I was wondering if you try to then reduce the final time, kind of force it to go faster and faster. Have you seen how the best fidelity kind of scales with that?
We haven't done that systematically. We haven't done, but we have, so I cannot say we did it systematically, but in certain cases, we found different solutions in different time by reducing the time. One of the things that is important to understand is that the way, I use the board, the way the algorithm works, it calculates the dynamics and the result over a certain window. And within that window, it will calculate it in a finite number of steps. So if this is your window, let's say up to here delta t, it will calculate it here. So one important point is that if your maximum, if this is your fidelity, if your maximum is here, and then you have, I don't know, another maximum that is exactly where your point is, this will be found, this will not be found. So things that we have done, for example, was then to reduce, you take a delta t prime and see, if you can. So we see that we can find solutions at different times with very high fidelity to these problems. We always tried by this fitness function, which tries to optimize both the time of the fidelity to keep the time within reason. So the order maximum of, let's say, 10 or maybe 20 times the inverse of 1 over J max. But we haven't done it systematically. This is very interesting. Again, that this is also something that would change depending on the network you have and of course, and the cast you have. What is your functionality, the one that you want to improve. But this is very interesting. We see that we find different, remember these are numerics, so we have the fidelity up to, we can have it up to, 99.99. That's because we use this for, yeah. But that's the thing. Yeah, that's a very interesting point. Thank you.
So further questions? I mean, if I take a different look, I know I'm very familiar with your work on DFT.
Okay.
And now we are moving towards the quantum computing. So what is your thoughts, or do you think that it will be possible in a short term to do DFT under the quantum computing?
Okay.
So how far you are from that?
First of all, I'm with Klaus, Vivian, and Raphael. We are organizing a workshop in Natal next week, which is exactly about basically DFT and the quantum technology. So looking at connection is something, this is actually the third workshop that we organize on this. So it's something that we looked at from a fundamental point of view, like, the role of entanglement in a function and density functional, or could you use DFT to calculate entanglement and how accurately and so on. I mean, there are different also the results from other people and so on and so forth. So it's something I'm interested for a while. What I know about this exact problem you are talking about is that now they are. So the answer is yes, in the sense that there is a lot of interest in hybrid type of computation, in which part of the computation is done using a traditional computer and part is done using a quantum computer. And because with quantum computer, they found, sorry, the name escapes me, but it's something related to finding, if you like, the ground state of your system. Minimizing a function, and they found a smart algorithm that helps with that. So I can write you more about this and then send you the exact name. I'm sorry, it's escaping. But the answer is yes, people are looking into this. So from the point of view of coding, and the root is this hybrid computation, bit quantum, bit traditional. Yeah. So there is a lot of interest in that. Yeah.
Perfect. So further questions? If not, let us thank Irene again. Yeah.
Thank you very much.